Welcome. This is working. Welcome all to this public defense, where Frans will present his work Improved Tooling for Digital Hardware Development, Spade, Surf and more. My name is Oskar Gustafsson. I will be the chair of this defense. So apart from Frans here, we also have the opponent, Martin Sjöbrell from Technical University of Denmark. We have an examination board, Martin Kuhm, Hoshulu Fulda, and David Broman from KTH Stockholm, and Daniel Axehill from the Automatic Control Department. We're also happy that our backup, Christoph Kessler from the Computer Science Department, is here. Thank you for that. So what will happen now is that Frans will present his work. Then we have a short break in case you only wanted to listen to Frans. After that, the opponent will discuss the work for some time. Then it's open for the examination board for questions, and then finally it's open for the public for questions. So that's all for now. Then there will be events after this as well, but this is the sort of formal part of the defense. So please, Frans.
That should work, right? Yes, I hear myself. Perfect. Thank you all very much for coming. I'm so happy to see so many of you here. I was afraid the room wouldn't be big enough, but it looks like we timed it or planned that perfectly. So I'm talking about digital hardware development, and I wanted to start off at a very basic level to give my non-technical audience members something to latch onto, but also because it nicely lays the foundation for the rest of the talk once we get into the more technical details. So if I want to make my laptop do something, I would need to program it to perhaps present some slides. Now, presenting slides is a little bit too complex to show on a slide, so I'll do a much simpler example of a calculator, one that just supports multiplication and addition. And then I would write a program in a programming language that tells the computer what to do. If we want to multiply some values, or if the user wants to multiply some values, set the result to a times b, otherwise set the result to a plus b. And the computer doesn't understand this natively. It doesn't understand what these things mean, at least not directly. But with a compiler, we can transform this into something the computer understands. So a sequence of instructions. The details here are super unimportant. Don't look too much at this if you don't understand it. But the point is, we write a programming language, we automatically transform it to instructions that the computer can understand and execute. And then we have our calculator. Now, a follow-up question that can appear is, how does the computer know, how does the silicon in my laptop know what these instructions mean? And it's essentially the same thing there. We have to program the silicon to teach it what following instructions means. And, well, that's also too hard to fit on a slide, but we can show a simple example of building a simple calculator chip. So we again start off by writing something in a programming language that describes what we want the hardware to do. So again, if the user wants to multiply, set the result to a times b, otherwise set the result to a plus b. And then, well, something needs to map it into the silicon that's roughly this size. And this is a fairly complicated process, well out of scope for what I've worked on here, but essentially we transform it into, well, the piece of silicon. The multipliers and the adders need to go somewhere on this piece of silicon, so some programmer will decide, okay, we'll put transistors that can do additions over there, transistors that can do multiplication over there, and the selection logic can be done with more transistors there. And then we can connect everything with wires, so A to the adder and to the multiplier, B to the adder and the multiplier, and then we can connect these to the selector, and now we have a chip that acts as a calculator. And if you wanted to make something more complex, say parsing or understanding instructions, you just write more code. Now you might be asking, why did I start talking about software and programming my laptop when this is about digital hardware development, doing essentially this process? Because the outputs are, of course, really, really different. One is a sequence of instructions, but the other is a chip and a physical layout and sort of transistors on silicon. But if you look at the input, they are very similar. Remove the begin and the end from the hardware part, and you essentially get to the software part. So then you might imagine that since these two are so similar, there should be a lot of idea sharing between the two. Programming languages for software should adopt ideas from hardware languages, and hardware languages should adopt ideas from software. However, that turns out not to really be the case in practice. And to demonstrate that, I want to show sort of the history of programming language development. This graph has one blob for all the programming languages with more than 5% market share today. The size of the blob is how many people use it today, and the location of the blob is the year at which these languages were released. So C from the early 70s is a relatively large blob. SQL is the other in the 70s. Most of the languages from the 70s and 80s are not really in use today, at least not by more than 5% of developers. But then in the 90s, we had a big explosion of a ton of new languages. C++, well, that's from the 85s, but the other ones, most of the languages you know about, like Python, JavaScript, Java, C#, even Haskell is from the 1990s. And then not much happened in the 2000s. I think there was still language development, but a lot of it didn't catch on, perhaps because we had a new batch of well-thought-out modern programming languages. And then in the 2010s, the software developers got excited about new programming languages, and a few new languages have sort of come up and are perhaps replacing the languages from the 90s, Rust being my favorite example. So this is the software world. The reason I'm talking about this is there's a lot of development here. Each blob represents some new ideas or some new combinations of ideas that makes development more productive, less error-prone, more approachable to people who aren't necessarily software engineers. And so, well, there's a lot of development there, but in the hardware world, the same graph looks like this. VHDL and Verilog are two big blobs from the early, or from before 1985. C++ is used in hardware as well via high-level synthesis, so that gets a blob. System C is from the early 2000s, or just before 2000, and System Verilog is also from the early 2000s. Now, personally, I would say that System Verilog retains so much of the core of Verilog that it really is a language from the 1985, even if it was standardized in the 2000s. The point of this is that we have all of these cool ideas in software that we haven't seen in hardware because the languages we used are predate these ideas. And so we are essentially missing out on 30 years of programming language development. If you've seen, you've seen the title or you've looked in the thesis, you'll know that this work is split in essentially 3 projects. The first one is Spade, a software-inspired hardware description language. Essentially, the past slides were the motivation for that project. While building Spade, we realized that if you raise the abstraction level in the language, you also need to raise the abstraction level when debugging. And so we had to build a new waveform viewer to accommodate these more modern HDLs. That project has taken off as its own project, independent of HDLs, but that's the sort of background motivation. And then there's a third part about Cinnabar and enabling domain experts to build hardware and hybrid electric vehicles. And hopefully the reason that's in here will make sense when we start talking about that. But we'll start talking about Spade. So again, a software-inspired hardware description language. And I have to admit I lied a little bit in my intro here. The calculator example does work. Those 2 pieces of code would work. But as you build something even a little bit more complex, you start to actually notice the differences between hardware and software, even in the programming language. And so you can't simply take a software programming language and apply it in hardware, at least not without much better high-level synthesis tools than we have today. So we need dedicated hardware description languages that allow you to reason about the things that we care about in hardware, but that are better than what we have now, and that's the idea with Spade. So if the motivation is software has a whole bunch of ideas, let's take them, but we also can't take them outright, what can we do? Well, I think we need to take the design philosophy behind these ideas and apply them in hardware. So what can we steal from software? One thing I really like about many modern software languages is the notion of fearless refactoring. Refactoring, of course, being a fancy word for the process of changing some code that you have to update it to accommodate changes to the specification, bug fixes, or perhaps just changing the code to make it easier to work with in the future. And this can be a scary process, because if you make a change to some part of the code base, you want to make damn sure it doesn't change anything over here or affect anything over here, causing bugs down the line. And this is fairly common, that you make a change here and you break something later, so you end up being somewhat afraid of making large-scale changes to your code, which is not great. Fearless refactoring is something some languages allow you to do, where the language has a bunch of guarantees that mean that if you make some change over here and it's going to affect some things over here, it is very likely that a compiler will yell at you and say, if you want to change this, you should also change this. And that way you can kind of mechanize refactoring and end up with code that still works after your changes. I don't think we can have truly fearless refactoring. You should be slightly afraid of refactoring, but you shouldn't be as afraid as you are in, say, Verilog. We also, sort of the big tool we have available to us as language designers is building abstraction. Abstraction can hide unimportant details that we aren't interested in, and it can highlight important details that we do care about. And it can also kind of reframe details in a way that we capture the core ideas that we care about and hide the unimportant details. I have two examples of this, one from software, one from hardware. In hardware, I think a good example is the abstraction around timing in digital logic. We have this Fmax frequency, that is the frequency we can reach, and that kind of encompasses all the capacitances and delays and so on in our circuit, and we can reason about it as a single number. Do we run at the desired frequency or not? So we hide the capacitances and all the analog effects behind a single number, which is what I love as a digital designer. In software, my favorite example of these abstractions is the Rust memory system, or Rust ownership system. The Rust developers realized that if you do manual memory management, you really run the risk of causing memory safety issues that are hard to debug and relatively costly, and can cause really big issues. You can leak a bunch of customer data, or you can cause a safety critical system to crash. So we want to avoid memory safety issues without paying performance. And so what the Rust abstraction does is it reframes the problem from we have a bunch of allocations, and then we hand out pointers to those allocations, and once we've created a pointer, we have no relation between the pointer and the thing it points to. With Rust, we instead have ownership, where we have a resource that is owned by something, and we can hand out a reference to that, but we have to make sure that the lifetime of that reference is shorter than the lifetime of the things it points to. And in doing so, we can eliminate memory safety bugs and guarantee that we eliminate a whole class of bugs with this abstraction, and then give a little escape hatch with the unsafe system in Rust, where you can still do the manual memory management if you really need to. The third thing a thing we need in a hardware description language at least is that we can't tolerate very much performance overhead. If our language is using twice as many resources or runs twice as slow as a competitor, it is not a reasonable hardware description language, because we have an implicit performance requirement if we're building hardware. If we didn't have this performance requirement, we would just build software. It would be easier and simpler. So if we then have a hardware description language that adds performance overhead, it's essentially dead on arrival. And finally, software in general has very good tooling. Modern software languages have dependency management that allows you to pull in external code. They have compilers that are not only there for compiling the code, but also for helping the user figure out issues, help the user reason about these abstractions, and so on. We need the editor integration and all that kind of stuff. And so that's something I don't talk a lot about in this presentation, but I think it's important to highlight that in order to have a successful programming language, we need the associated tooling so developers can actually work with it. If we just have a great, well-designed language without the tooling, it's not going to work in practice. So now I've talked about very abstract things for quite a while. Let's get concrete and talk about abstraction, namely the pipelining abstraction in Spade. This is one of the first things I did, and it sort of brings this idea of reframing a problem to highlight the important parts, namely the pipeline parts, and hide the unimportant parts, like exactly what is the name of every register in a pipeline. You can see I have some code on the left and some hardware on the right. And the code has a few unimportant details, but the important details for this presentation are the first pipeline of 2, which specifies that the latency of this pipeline is 2 clock cycles. Feed the data in at clock cycle 5, and you get the data out at clock cycle 7. The compiler could infer this from the body, but it's helpful to have it in the head. One, as a developer, is to see that this is what I want, check this for me. But also, if you instantiate this pipeline elsewhere, you don't have to look inside the body to figure out what it does. You can just look at the head and get all the important semantics of the pipeline. The other 2 important statements in a pipeline are the reg statements. And what a reg statement does is take every variable above the reg statement, feed it through a register, and then when you refer to that variable later, you refer to the register version. And you can see these 2 reg statements over here correspond to the 2 purple lines of registers in the graph. And so this is how the pipelining abstraction works. This is really nice when you're building your pipeline because you don't have to add a bunch of intermediate registers and keep track of them, but it is much more helpful when you have to make changes to your code, coming back to this idea of fearless refactoring. Let's say we build this and then we realize that the G block over there at the top right is not good enough. It is perhaps running too slow, so we need to pipeline it, or perhaps the requirements change, so we need to do more in the G block. Whatever the reason, we change G to accommodate these new changes, and now we've refactored part of the code, and we're going to be affected, because the change looks like this graphically. And if you look at this graphically, you can see that that this will not behave as it did before. My sort of controversial opinion about this is you should never have to look at a graphical view of your circuit to figure out if it will work correctly. And so with Spade, if you make this change, you compile it. The compiler will first tell you that this instantiation of G is wrong. You can't instantiate a function as a pipeline as a function. You need to specify its latency. So you add the inst of 2, and you get and the compiler will be happy with that part. That, of course, hasn't changed anything. The language could omit this and just do the rest of this analysis anyway. Because the real problem here is, of course, this backage, the red one, that feeds back through a pipeline stage, and that's going to break everything. Because the compiler is aware of what latency means and what pipelines means, we don't actually have to look at the figure again. We can compile the code. We get an error message that says the variable x is used before it's ready. It's coming out of a pipeline stage. It won't be available for another stage. And so you need to make adjustments. In this case, the most likely adjustment you would make is adding a second line of registers like this. And because we have registers and pipeline stages as a construct in the language, making this change is very simple. We simply put another reg statement here, and we adjust the latency of the outer pipeline. And in that way, we've retimed this circuit without having to think about what we need to do. The compiler told us what to change, and we essentially followed it along. In a more complex pipeline with feedback, we would have to think a bit, but here we don't have to think at all. And this applies recursively. We've now changed our pipeline to have a latency of 3 instead of 2. Whoever instantiates this pipeline now also needs to accommodate that change. And by the time the whole project compiles, we're back to a working system. Fearless refactoring. So that's the pipelining abstraction. Another thing Spade has, which is fairly unique, is a very powerful type system. If you're familiar with Rust, it is essentially the Rust type system, not including ownership. And that means it has structs and tuples as compound types. It has sum types via, or what is called sum types via enums in Spade. It has powerful generics that allow you to have a type that is parameterized over another type, unlike the VHDL generics that only allow you to have a generic that is essentially how many bits do we have. We can retain the type information through the generics in Spade. We have lambda functions that allow you to be generic over behavior, and then we have overflow-free arithmetic, which is a hardware-specific thing. Everything else is essentially a normal software type system. But the overflow-free arithmetic means that if you add 2 3-bit numbers, for example, you get a 4-bit number out because you could have overflowed those original numbers. And the compiler adds these, and if you want to throw away that additional bit, you have to do so explicitly. So you never throw away information on accident. I want to talk briefly about these sum types because they are fairly unique for a hardware description language. And I want to do so with an example of an option type. This is defined in the standard library, and it is extremely helpful. So an option, an enum in Spade, like an enum in VHDL, has a few different variants, and it's one of these variants every time. So either it's none or it's some. But unlike your VHDL or C enums, there is a payload associated with these variants. In this case, none has no payload, but some has the value of any other type. And this is essentially a valid signal that is bundled with the data it validates. So the compiler ensures that you don't check val unless you know that this data is valid. It might make more sense for the hardware people among you to see the sort of bit representation of this. We have a tag that is either 0 or 1. 0 means it's none, and then the rest of the bits of this value are undefined. They could be whatever. And if the tag is 1, there is a value present, and that's sort of the normal representation of that value. In this case, a 5-bit integer. So this is helpful when designing, using this, we can build abstractions inside the language. So we can use the type system to extend the language with new abstractions, for example, around streams. Because a stream in hardware is essentially just a signal that is sometimes valid, sometimes not. In this case, we have a stream of bytes that is coming in, and that stream represents some packets. And we want to transform it into packets and take some information out. So we take this byte stream, we run this into packets function or method to transform it into the packets in this protocol. It should probably be, this method should probably be called into CSI packets, but that's unimportant. We can then filter these packets to only look at the packets we're interested in. In this particular protocols, we want to look at the header and see that it's a 0x2A packet. That's the pixel data we're interested in this case, and then we can take the pixels out with these methods. And so what happens behind these method calls is sort of out of scope for here, but the point is that by building this stream abstraction, we can have independent reasoning about what transformation we want to make on the stream, in this case, filtering out a bunch of packets, and the sort of data sequencing and validity that is kind of hidden behind the method calls, but so the type system separates the two, just like the pipeline separates the computation from the pipeline stage details. Now that we have a bunch of abstractions in the language, we're able to communicate design intent, both to the user and to to the compiler. So to programmers, having all this design intent available mechanizes refactoring even more. For example, if you had a unit that previously produced a value every clock cycle, but now you only produce it some clock cycle, you change the type from T to option of T, and the compiler will tell you everywhere that could affect things, and you have to accommodate this. To the compiler, when we have design intent available, we get some leeway in changing the behavior to still accommodate this design intent. And this is something we only started exploring towards the end of my work here. But one example, or the primary example we've been looking at is, again, signal validity. So we have these option types that communicate when data is valid and when it isn't valid. And an interesting property of invalid data in hardware is that if you feed data through a circuit, even if it's invalid, it's going to switch all the transistors to these values that we don't care about. That's going to consume power. And so ideally, we want to turn off the circuit in the clock cycles where it's computing on unimportant details. And that's clock gating. In principle, the way it works is instead of having hardware like this, where we just feed the data through the computation after a register, we can transform this into feeding the tag through as normal, but instead of feeding an invalid value through, we feed the previous value back into the register. And that way, this multiplier will only have to switch values on valid data. Of course, this multiplexer will have some cost, but in practice, synthesis tools in ASICs will convert this to a clock gate for the registers, and in FPGAs, this will become a clock-enabled signal. So this is, while we generate this code, the synthesis tool will then change it to a more efficient version. And the results of performing this optimization, or I should say one more thing before that. This is an optimization we could do manually, of course, but doing so for every register in the design will become very, very tedious after a while. And it also doesn't enable design space exploration. We have to commit to making this change if we want to make the change, but if it's a compiler optimization, we can simply turn that on or off depending on if it works. Or if it gives better result, it will still produce the right results. So in the real world, this allows us, in a real world example, this allows us to go from 20 milliwatts of power down to roughly 14 milliwatts of power. So pretty nice saving. We can also have a more contrived example, which is essentially a SIMD dot product computation, where we represent zeros as an invalid data, and that way we can turn off multipliers that are going to multiply by 0. And essentially, on the left, we have no optimization on the right, we have optimization on, and depending on the sparsity of this data that is coming in, the probability of data being valid or 0, we can completely remove the static dynamic power consumption of this circuit when there is no valid data. And of course, we don't save anything if there is constantly valid data, but we also don't really lose anything. So if you're sparse, sometimes this would still be a valid optimization. And of course, because this is an optimization we can turn on, we can turn it on, see what the effect is, and keep it if we like it. So that's most of what I wanted to say for Spade. Again, it has fearless refactoring via the type system and abstractions that are built for hardware. It has low performance overhead. You could even argue that it has negative performance overhead once we start doing optimizations, though that's kind of debatable what that means. And then it has, again, really good tooling, which I won't go into details about here. If you want to learn more about Spade, in the thesis, we have paper A introduces the language as a whole. Paper B talks specifically about this clock gating optimization. And then paper C starts talking about debugging, where we integrated Spade with a language built by a friend of mine called Val. And that nicely leads us on to debugging high-level HDLs. As I said, when we built Spade, I realized that as you raise the abstraction level of your language, if your debugging tools are still at this lower level of abstraction, the gains you have from having the abstraction available when you're designing are lost when you have to translate between abstraction levels when debugging. That is a super tedious process. And so to exemplify this was the original problem Surfer was meant to solve. Let's say we have these Spade types, a signal of this type, so a memory command has an address, has a command. The command has itself is an option, and then is one of these op things. If we just look at this in a conventional waveform viewer, which is the go-to debugging tool for a lot of hardware projects, it would look like this. How many of you would like to guess what 017XX means in terms of these values? Notice how I'm not raising my hand either, because I wrote the compiler, I should know how to translate it, and in principle I do. But when I'm debugging, I really don't want to do that process for all of these values. So what Surfer can do is translate these values into values that have a lot more information in them. So the command with Surfer, with the translator enabled, looks like this. You can see it's accessing address 5, it's first reading for 2 clock cycles, then it goes to no command, so it's not interacting with the memory, before writing the value 10 to 0. And that's a lot more information than you get from the top trace. So Surfer is a waveform viewer, like I said. As far as waveform viewers go, it looks pretty standard. This is what it looks like. But we realized, once we started building it, that there's apparently a need for a new open source waveform viewer that is better than the alternative. And so this project has taken off. There are many users of this project, several contributors, and it's being integrated in quite a lot of projects because it is both extensible to support new translators and new workflows. So we have support for more HDLs than just Spade, for example. And it's embeddable inside other projects. So it uses WebTech and can be embedded in a lot of stuff. And that means that sometimes I get emails saying, hey, we're about to launch a new project for our startup. We're using Surfer as a key component. Thanks for building it, which is really cool to see. So Surfer is probably the most successful project of the three, but it's also the one that's least interesting to talk about here. So that's all I'll say for that. If you want to learn more about Surfer, paper D is our paper that introduces that project. Moving on to Cinnabar then, and for that we're going to switch gears and talk about hybrid electric vehicles. And why we do that will become apparent in a few minutes. For now, just roll with it. So what is a hybrid electric vehicle? It's a vehicle that has both a combustion engine and an electric motor, and we can use both. When I started this 6 years ago, my impression of hybrid electric vehicles was you use the electric motor to get to work because you have a short commute and the battery lasts, but if you want to drive further, you would start up the combustion engine so you can get longer than the battery allows. In practice, that turns out not to be the case. I think it's very uncommon for hybrid electric vehicles to completely switch between the two. You essentially always use both. In fact, this thing where you plug in your hybrid electric vehicle and charge it up is not something a lot of hybrid electric vehicles support. The battery is only there for energy storage. And so you might think, why would you put a battery in a vehicle that you cannot plug in and charge externally? But the reason is you can conserve energy and use it later. So let's say we're driving along this flat piece of road, and our motor is sort of producing less power than it would at its optimal, at its peak efficiency. And well, we can't really do much about it if our road is just flat. But if we get to a hill later, we're in the opposite scenario. We're now need more power than the motor can produce at its peak efficiency. And so what we can do with the battery is when we're driving on this flat road, we can run the engine harder, charge up the battery a little bit, and store this energy for use later. So the engine is now operating at its peak efficiency. And then once we get to the hill, we can use the energy in the battery to offload the combustion engine so it can still operate at its peak efficiency. And in that way, we've saved a bit of fuel. Now the question is, how do we figure out when and where to use the combustion engine in the electric motor? And to do so, we can run an algorithm, an instance of dynamic programming. So we have the road we want to drive. We look a few kilometers ahead. This is not like the final destination. It's just a destination a few kilometers ahead. And then we think about, okay, what will our velocity be on this road? And we have speed limits and stop signs, of course, here. What we can do then is work backwards. So we assume we get to the destination. Once we're there, it doesn't cost any fuel to get there, and it doesn't take any time to get there. So we can just say, okay, that is free. We're there, we're good. And then we start simulating backwards and say, okay, we can get to the destination. How do we get to the destination from these points? Well, we simulate some inputs to the vehicle. We can accelerate a lot, cost a bunch of fuel, go above the speed limit, get arrested, not great. We can brake a lot and charge up the battery, but it also doesn't get us to our destination. So in this stage, it's pretty simple. The cost is essentially, we simulate all the inputs in all the states, and we see that the best option here is to have as much energy as available as possible. Then we can just glide down to the destination. But of course, how do we get to those points? Well, we can do the same thing. We look at the states or the distance one step to the left. We simulate some inputs, and in this case, things get more interesting, because we can brake a lot here, save a bunch of fuel, but then we get to a costly state because we have to accelerate back up to the destination. We could accelerate a lot and go above the speed limit, or we could accelerate a little bit and get to this cheap state in the future, but then we've paid here. And so again, we can simulate all the inputs, add the cost of the state plus the cost of the input, and figure out what the cost is. And it would look something like this. Have as much energy available as possible, unless you have too much available, and then you can't brake. And now we can work backwards, filling in this plot until we get to the start. And then we get the sort of route we want to drive along. So we work backwards, we fill in the grid, we follow and then we can figure out what route we should take through the grid. In a hybrid electric vehicle, we of course also have a state of charge on the z-axis here, so this becomes a more complex problem. And it also becomes a problem we might want to run more often. In this case, if we just have static stop signs and speed limit, we could pre-compute all of this and have it update in the vehicle occasionally. But ideally, we want to take into account more things. Maybe we have a truck that we will catch up to at some point, and that dynamically changes the speed limit. If we catch up to that truck with a plan to keep as much speed as possible until we get as late as possible, then that plan has failed when that truck comes along. Or we could have a traffic light that sort of changes dynamically, of course. So the point is we can do a better job optimizing this by taking into account traffic and things that vary often. So this, to perform this computation, we need to evaluate every input in every state at every distance step we are interested in. And that ends up being roughly 2.4 billion evaluations of the model. And a model evaluation here means taking some sort of torque requirement to the vehicle, simulating what the combustion engine will do, what the electric motor will do, what the gearbox will do, and so on. So it's a fairly complex computation. On my desktop Xeon CPU, that takes about 120 seconds to complete these 2.4 billion evaluations. So if we want to take into account traffic, we'll probably have passed that traffic by the time we figure out how we should have overtaken them. For real-time use, we should aim for roughly 2 seconds. And so we're quite far away from that with a CPU. And that is a perfect reason to build custom hardware, because custom hardware can accelerate this and perhaps reach the 2 seconds for real-time use. The interesting part from a hardware design perspective is that we now have a domain expert in the vehicle domain that knows how to model a vehicle, knows how to take the specification of like, this is the engine we want, and figure out how to model that in a way that makes sense. And then we have the hardware engineer who knows how to implement this in hardware, because hardware is hard enough to design that most vehicle experts can't do it on their own. The problem with that is if the vehicle expert does their model development, only then can the hardware engineer start. So we sequentialize the process, and if the vehicle expert realizes that something needs to change in the model or the specification changes, perhaps we develop a new vehicle or we want to run this on many vehicles, the hardware engineer has to redo a large chunk of their work. So as an alternative, we propose that we build the vehicle model, hardware for the vehicle model, and this thing is relatively simple from a hardware perspective. It takes a state, it takes an input, it computes the next state and the cost of that state. And again, this is relatively simple hardware. It doesn't have any feedback in the computations. We can pipeline it to our heart's content. And it's very heavy on the vehicle details. So it's helpful if the vehicle modeling expert can be as involved as possible in this process. And that makes it extremely suitable for high-level synthesis. So we propose that the vehicle model we build with high-level synthesis. In the meantime, we have the scheduler that decides what inputs should we feed to the model when. We have some memory manager and the thing that adds the cost of the input, the cost of the state we reach. And all of these things are, from a modeling perspective, relatively simple. We are largely independent of the vehicle model here. And they're heavy on the hardware details. Getting this to work with the sort of fully pipelined vehicle model that we want takes some effort. So it's very suitable for a manual implementation, perhaps with Spade. And so that's sort of the workflow we propose, and we show that by doing this, high-level synthesizing the vehicle model, and then manually implementing the scheduler and the memory, we can accelerate this computation, run it in these 2 seconds with real time, and we can even do it in a configurable way, so you can have a configurable number of instances of the vehicle model to tune performance versus resource usage. Finally, briefly, I want to mention Cinnabar. It is a name that has appeared a little bit, and it is sort of central to this as well. It is a high-level synthesis tool, which, unlike traditional high-level synthesis, which has to support arbitrary software and needs to do scheduling and sort of dynamic loops and so on, where you also need to do manual word length selection, unlike the traditional HLS, Cinnabar is restricted to fully pipelined model. So an initiation interval of 1, that means you can have no feedback in your model, you can have no data-dependent loops, you can have if statements, and you can have sort of fully unrollable loops. But in doing so, we simplify the high-level synthesis tool so we know what we will get. And then because we're also doing an optimization thing, it's fine to have a little bit of error in the output compared to the sort of reference model. We're not even sure if the reference model accurately models the real vehicle. So we can allow a designer to choose the word length that is used for different parts of the computation in order to trade hardware resources for speed. Sort of abstracting away the exact data types that you would otherwise have to decide in the traditional HLS model. So that's Cinnabar. It can be used for the vehicle model here. And with that, we get to the end of the presentation. So for Cinnabar, we have paper E that introduces the problem. We have paper F that talks about how we can compile LLVM bytecode into pipelined hardware. And then paper G talks about this integration between the high-level synthesized model and the rest of the system, and shows that we can actually run this vehicle optimization algorithm in real time. So with that said, thank you very much for listening. I'm super happy to see everyone here, and I look forward to some interesting discussion.
Thank you, Frans. Let's take a short break, and we could meet at 10 sharp again. We'll set things up for the discussion. Welcome back. Now it's time for the opposition, where Martin Schöbel, the opponent, Technical University of Denmark, will discuss the work with Frans.
Okay, thank you for the introduction, and very much thank you for the very nice presentation and also good work. I really enjoyed reading it. It was good reading stuff. And I mean, I don't know so much about Git.
I think we should wait for the rest of the examination board that apparently
Yes.
I missed.
Where are they?
Could be an important detail.
I was just starting thanking for the presentation, so writing. So I'm waiting for you guys. And also, I'm very impressed at the 2 active projects. I mean, it's not so common that something real is after a PhD thesis. And I don't know about GitLab because I'm used to GitHub. I see 130 stars. I assume this is a lot on GitLab.
I think so. I don't know the number either, but it's more than 1 star on GitLab is more than 1 star on GitHub.
Yes, I think so. I think so.
Yeah.
Yes, I think it's a lot of engineering work which went in, which some people say it's not scientific, but I really appreciate engineering work as part of a PhD thesis, doing real stuff. And you also did a decent number of papers. 10 papers are very good for a PhD thesis. Let's start with questions.
Yeah.
Actually, you answer the first question in your errata. What is paper A? It's paper A. Why is it submitted something? So you say it's already accepted?
It's conditionally accepted.
Conditionally accepted,
No.
but you didn't write and say, okay, we submitted it and here and there. What about paper B? Is it submitted? What about paper F? Is it submitted?
So paper B is not submitted. We should submit it at some point, but I've done other things. Paper F probably won't be submitted. It's hard to... The problem with that work is we had to do the work to figure out how we do this transformation, but we realized that conventional high-level synthesis tools probably already do this, but no one explains how to do it. So we figured we'd try to write a paper saying, hey, this is how you do it. We know that this is kind of done already, but no one has said it. But that angle didn't work, and sort of rewriting that paper in a way that... yeah.
I think it would be nice, gentlemen, it's already too late, to state what the papers are about. I mean, will be submitted, okay, we just wrote a technical report, we will not submit it somewhere. Or at the end, having a full publication list. I mean, I can always type your name, Google Scholar, I get the publication list these days.
No, we should have perhaps had more details than just manuscript, which I think is what it says now.
I very much appreciate, which it resonates a lot with me, that you try to bring software practice into hardware design, and I'm very much on your thing. But I find it very hard to convince companies to change the ways of work. I'm teaching Chisel since 2020, and people are still using VHDL, Verilog, Perl for generating VHDL code. I've seen this in companies, and do you have any experience how you bring at least the mindset of software engineering into hardware companies?
I think it's hard in general. Even in software engineering, it's very hard to convince someone that a new language is better. And there's some blog post somewhere that I read a while ago of like, every time you want to say something like this abstraction is better than what you have before, it's very easy to be convinced of that when you've used the abstraction. But when you're used to writing assembly, you're like, oh, I have all the control. I know how to do everything, so I shouldn't go to C. And then you finally convince someone to go to C, and then it's like, oh, we could have
There's
more
a very
abstraction.
famous paper about it. You can only assess what you have done and don't can look up. Yes. Yes.
And I think that's a problem in the hardware world as well. And perhaps there people are even more reluctant to move to a new language because that also doesn't happen. Everyone uses Verilog or VHDL.
Yeah.
I think what has worked in a lot of software languages is kind of a grassroots thing. You won't convince a company to start using a language directly, but perhaps you can convince some hobbyists to start using the language and be sort of ambassadors. And I think I've tried doing that with Spade, so I have a few people now that are hobbyists but are excited about the language, and perhaps that's the way to grow it.
Or maybe it's startups.
Yeah, startups could
Like
also work.
Sci-Fi doing Chisel, for example.
Yes.
Though you have a nice background chapters, very nice to read and give a good overview of hardware languages. One question, what about verification?
Yeah.
It's not mentioned in the background at all.
Didn't I have a single section on the
maybe a
verification?
paragraph, but,
Yes.
but not as a chapter.
No. That is, the problem is I don't know how verification works. We don't really teach any verification here.
Wait a second. Verification, I mean testing, not formal verification.
Okay, yeah.
Testing. Test benches trying to check what the hardware is doing.
I could have written a bit more about non-formal verification. I guess in this case, the Spade solution, or Spade is very much focused on design, and then verification is, we just use CocoTB or very later. So I guess I didn't consider it that important for the rest of the work, but I think I should focus more on verification because that is still
maybe I'm jumping in. I have a little bit later on Spade and verification. You say, okay, it's almost not mentioned. It's a few sentences. Okay, we use CocoDB and Verilator on the generated Verilog code. Then you lose everything from Spade. You have just you're back down to your string of bits. Where do you see your types? In
so
verification?
that is a problem we have solved. We have an extension, a library around CocoTB that allows you to write a string that is a Spade expression, and then it goes to the Spade compiler and compiles this into the bit
string based. That's not very type safe.
It goes through the type checker. So you write some Spade code, it type checks that Spade code, and then it generates the bit representation of that, and it knows what the input and output types are of the design and the test. So it is type safe.
Okay.
It's just that you get the Spade type error as a runtime error in Python or as a runtime error in Verilator.
Yeah. And also still on the background, what about VHDL and System Verilog? You almost not mentioned those two languages in your background thing. I agree, it's old language from the 80s, but...
Yeah.
Can I integrate my legacy's VHDL code with your Spade
yes.
language?
Absolutely with Verilog, since Spade emits Verilog, and you can have an external and a module marked extern, both to get Verilog code into Spade and to get Spade code into Verilog. Yeah. VHDL is a bit more tricky. We don't have a VHDL backend, so you would have to go through whatever you use to go from Verilog to VHDL. But you can absolutely interoperate the two. And I think that also comes back to the first question you had of industry adoption. I think that's almost required. You want to give the industry some way of like trying it out on a small example, and then having good interoperability is important.
I mean, I think on the industry case, we need to convince them somehow that Spade or Chisel or whatever is a hardware generator language. So they do generation in Perl, as I mentioned before, or Python, or TCL, whatever, writing script code to generate code in strings.
Yeah.
And maybe you can sell it that, okay, Spade or Chisel is a generator language. with type safety and not strings.
Yeah.
On Spade, yes, it's a very nice syntax to express pipelines. Yeah. Decent if you do a forward pipeline. What if you have a cycle back?
Yeah.
It becomes a little bit nasty, I guess.
It does. So some of the guarantees go out of the window there. The sort of guarantee about latency, of course, goes away because there's no well-defined latency when you have when you have feedback. What you do get is you still get the sort of description of what happens in every stage, and you can refer to a variable. Say, I want X from the stage up here, or I want X from 2 stages above me. So you get some help in describing the pipeline, but some of the guarantees that you can refactor completely mechanical do go away.
Related to this pipelining, so pipelines, in my head, is just a process of pipeline. Though I'm missing in the paper, in the thesis, use cases. Well, why not just, okay, I sit down, write a RISC-V pipeline, 3 stages, 5 stages, whatever, in Spade, and then take IPEX from ETH Zurich and let's see, compare it. I mean, I assume that the code generated is not bad. I mean, it's still RTL, but having the case, I think someone was asking yesterday about performance and area and comparing those 2 solutions. So first, what is the efficiency of Spade? And second, how do you do real pipelines with branches going back, with forwarding, which is actually going back in the process?
Yeah, so for the first question, we've done a little bit of experimentation of comparing resource usage. It's a very hard thing to compare because you kind of, on the one hand, you want to like write the idiomatic Spade code and the idiomatic Verilog and compare those two, but Spade then sort of encourages you to write things in a specific way, and Verilog might encourage you to write in a different way. And then we might have a difference in resources and performance, and is that then down to the language having overhead, or the sort of the exact way you wrote things having overhead?
I think that is okay. I mean, if it's idiomatic to write this way in Spade, then this is the way to go.
Yeah. So
you could also compare, okay, how long does it take to me to write these 2 things?
Yeah.
This one takes 1 day, the other one takes 3 weeks.
Yeah.
Yes, this is harder to compare.
Yeah, so the few comparisons we've done, it's like around the same things, or around the same resource usage and performance. Spade is sometimes a little bit better, Verilog is sometimes a little bit better, and then it's comparing what I've written or what a few students have written to existing off-the-shelf implementations.
I think you should do a paper implementing a RISC-V processor with Spade.
Yeah.
Maybe a little bit tough to publish, but there are possibilities.
Yeah. The second question about the pipelines.
Yeah.
I would say a processor pipeline is probably the worst use case for the pipelining construct in Spade, because there is so much feedback and so on. It's more suited for this computation pipeline, like I had in the vehicle model. We want to do a whole bunch of computations. When and where do we do those? And perhaps in the processor pipeline, you still get this help of like, when you do forwarding, you can just say, is the next stage or the next stage, oh no, sorry, that's stalling. Is the next stage or the next stage a jump instruction, then stall? So you still get some help in like referring to variables from other stages, but there's so much feedback and so on that.
But for just forward pipelining, current tools can do the retiming for yourself. So you put let's say you're writing multiply in VHDL, and you put 3 or 4 registers at the end.
Yeah.
The synthesis tool does retiming for you.
Yes. My impression of that is FPGA tools do it on DSP blocks, and not much else.
But you don't have to do anything. It's just writing some registers, and whoops, it does a retiming.
Yes, but only for DSP blocks, right? It's not for arbitrary LUT logic. I don't think conventional or FPGA tools do a lot of retiming. Okay. Do they? I know ASIC tools do retiming. And if that is the case, there is an advantage to having this pipelining thing. If I often write my pipeline, have a multiplier in there, and then realize, oh, I forgot that I need these 3 pipeline stages at the end. And in Spade, I can just put them after the multiplier, and it will generate this thing that will get sucked up. But the rest of the system that accounts for latency will accommodate that change without me having to think about it. So if the FPGA tools do full retiming flawlessly, then yeah, the pipelining thing is less important. But
yeah, I think, okay, we talked about tests. It's CocoDB invalidator. So is there no assertions in Spade or something helping?
there is
testing?
technically an assertion statement, but I haven't used it in a while, and it's very much not as powerful as the assertion statement in System Verilog, for example.
Yeah.
So no, it's there on a technicality, but it's not. I think what a verification engineer would expect.
Okay, the System Verilog assertion is a completely different topic than all this stuff. What about hardware generators? What writing hardware generators? Like in Chisel, we use Scala, using functional programming, you generate some trees of multiplexers or whatever.
Yep.
What can I do in Spade in relation to generators?
Yeah, so first of all, I think if you want to build a big generator thing, you should use Chisel or Spinal or something like that, which is designed for it. So Spade can do some hardware generation now. It's all done as recursive instantiations of things. So you have a unit that is perhaps, if you have a tree, it's parameterized by the size, the width of the tree, and then you instantiate a recursive call for half the tree in each branch, and so on. So it's a very functional-like
So
approach.
do you regret a little bit that you do the whole language in itself instead of just making embedded language in Rust? Do you like Rust?
I like Rust. No, I don't regret that. I think there is absolutely a reason to do these embedded languages because you get all this hardware generation stuff. But doing my own language has allowed me to. I think the pipelining thing would be very hard to do in a generator in the way I've done it, where you just redefine variables.
Yes.
And then I can do error messages that I have full control over. I don't have a runtime error where I need to figure out what source line fix this. I don't have the maybe minor issue of having all the good syntax taken up by the host language.
Yeah.
So you write
yes.
when instead of if in Chisel, for example.
Yes. Yeah.
So I think the generated languages are really good, and I'm happy they exist. But I hope that the end in 30 years that we're not stuck with only generated languages. I think we want a custom languages for the case where you don't need so much generation. You're more interested in, I want to build this specific architecture that isn't super sort of generic. And then I think it's good to have something like Spade.
So how large is the community in your new language? It's always hard to establish a new language. What projects exist? I haven't checked out. There's no link in your thesis on projects using Spade?
We had a project list on the website, but I didn't keep that up to date. So you didn't miss anything. I actually removed that because I didn't keep it up to date. So I think I have a Discord community. A friend of mine convinced me to make one of those, and I think it has 250. We passed 256 members at some point.
That's cool.
It's a lot of those members are very inactive, but there's also a few members that are very active and are discussing. Some are using the language. A lot of them are also discussing language design, like how should we do this in the best way. Some people in the audience here are some of those people, and then there's online people who are also in there and discussing these language changes and so on. So. It's small but active, I would say.
Yes, a little bit more detail. So, can you have structures as arguments and as return values? I didn't really want it. You can return a tuple from a function.
You can return a tuple. You can return a struct. You can return an enum. Any type can be returned.
Then you have a full paper about arguing for the option type to be type safe on the valid. But most of the time we need two-way handshake, ready valid.
Yeah.
The option type is only giving a valid. You have some version of you have an option and an option for the ready valid. Maybe we need something else and an option for having ready and valid.
Yeah. So at least with my experimentation, and I've written quite a lot of ready valid handshake stuff in Spade now, it works quite well that the ready valid type is a struct that contains an option for the valid path and then a ready signal that goes backwards.
This sounds for me a little bit of inconsistent. Okay, so you have the option for the valid,
Yeah.
which is type safe,
Yeah.
and then you have a signal for the ready, just a plain signal as we had it before, ready valid.
Yeah. So the compiler does ensure that you at least set this valid or this ready signal when you instantiate or when you use these. It's this linear type checking and port things that we mentioned in the first paper. Okay. And essentially, the way the system works is it keeps track of all the inverted wires, which is our term for a wire that goes in the opposite way of the normal flow of information. So if you take an inverted wire, you essentially have an output from your module that is in the input position. Yeah. And then there's a linear type checker that looks at all the inverted wires and looks at where they are being where they are set or passed along to someone else. And if you don't pass this wire along to someone else or don't set the value at all, you don't pass along the value or set the value at all, then it complains at you. And it also complains if you set the value in two different places, because then you'll have like an undefined value.
Okay. So this combinator paper, is this published or?
Paper B or?
What is this?
Yeah, I think that's the combinator paper, I guess.
This is published or what?
No, that one is still a work in progress.
Then I can influence the paper a little bit.
Yes, please do.
Though, because the title is about options, and then you're talking about the map, which has nothing to do with options. I think you should have a more generic title on this paper.
Okay, yeah. I would claim that the map is at least applicable to option, even if it's used in other...
But the idea of map is something different. It's about the generating hardware, and option is about the valid signal. I would change the title.
Okay, because I view the idea of the map function as transforming the inner value while retaining the sort of outer value, and the inner value then being whatever is in the option, and the outer value being the tag. So the map function allows you to take a signal of option type, say bytes, and transform it into a struct or something like that.
So the map needs to have an option?
No, you can implement the map on
Could
other
you just have
types.
a string of adders as a map, right? Or another increment.
No,
whatever.
so it's not...
What we reduce.
You could map over an array as well.
Yeah.
And essentially, because the array also has an inner value, it's sort of the outer value, which is the full collection, and then you have the instances of the inner value, and then the map function, in that case, transforms every inner value.
Yeah. Not option specific.
No. That's, I think I see your point.
Make a larger title.
Yeah.
On extension of spade or whatever, what types. Then you have a paper on waveform analysis.
Yep.
Which I'm very unused to because waveforms, you use them for debugging, you look at that, you stare at them. I've seen people having large screens for staring hours and hours on waveforms. Yeah. And I talk to my students, yes, waveform looking is not testing, it's debugging. Okay,
yes.
It's just so why do I need to extract information from waveforms? Why can't I do it in my test bench itself? What's the point here? I mean, if I want to find a pattern, okay, this happens, does this happen 10 cycles later? Can't I just express this in my test bench instead of expressing it on top of waveforms which are generated after my tests run?
Yeah. So I guess there's a few reasons for that. One is then you have to do this analysis or I guess you would use Chisel, but you would have to do it in the host language. And the host language...
Just a Verilog, whatever.
Yeah, the HDL would need to support all this, which I guess most, at least existing ones do. But the bigger problem, I guess, is if you realize, I want to actually check this thing as well, now you have to resimulate your design. So having this done on the waveforms afterwards allows you to sort of iterate on exactly what you want to look at without having to recompile. So you get a faster cycle of finding this information.
I don't say it's bad. It's just very new for me. I never thought about, I could actually programmatically analyze waveforms.
Yeah. No, I think it's Lucas, who was my co-author on that paper, is like one of the only people who are doing this sort of thing. And I think it's an interesting technique. I think it does have a disadvantage of quick iteration time in the information extraction.
Just another tool in your toolbox. Yeah.
Yeah.
Yes. So we were very quick, I think. So a very short question on Cinnabar. We also had a very short presentation. So it just supports forward pipelining?
Yes.
No feedback, no nothing?
Nope.
Okay. Yes, the weekly modeling itself is kind of off topic for me.
Yeah. For me as well, almost.
So, yeah, I mean, I didn't take my hour as assigned. So I'm ending up in some general questions, not technical questions. What about bringing some of your ideas from Spade into a different language? You know which one I mean. The Chisel
I'm guessing
community.
you're hinting at Chisel.
Yes, of course. A little bit larger since the Spade community.
I think some of them could be brought over. I don't know how easy it would be to say integrate the whole
It's an
type
option
system.
thing, for example.
Yeah.
That would be very nice.
Yeah. No, that could absolutely be ported. And I think that's kind of the point of the option paper. It's not only this is something we can do in Spade. It's more like this is something we should do in all HDLs where we can do it.
Yeah.
So yeah, my main goal is to get a better HDL, whether that is Spade or another HDL that has the features I want. Is like doesn't matter to me. So I would be happy if Chisel adopts them.
Yeah, I mean, language development is not easy. It's a lot of political stuff.
Yeah.
Involved in the discussion on Chisel. And, yeah.
Yeah. In that way,
it
it's
has
very
topics
nice.
I don't talk about.
In that way, it's very nice to have a community of only 200 people, so I can do what I want.
Exactly. Yes. So you're starting as a postdoc in Munich?
Yep.
What are you doing there?
I'm continuing my work essentially, so I'll get to work on both Spade and Surfer and make them better.
Yes, this is my next question. What do you continue on Surfer? Will it be a product?
Surfer I don't think is dying down, and Surfer has the advantage of having several people on as contributors. Oscar, for example, he has more commits on Surfer than I do at this point, and we have a few other people. Lucas is also a contributor to Surfer. We have some external people that I don't think I've met in real life that are also contributing significantly. So I don't see Surfer going away anytime soon.
Actually, I just realized I skipped all Surfer questions here. All right. Okay, then I have to have some more questions. First of all, I think I will switch to Surfer in my next digital electronic tool in spring semester. And what is the support about Chisel? Yeah, so the Chisel support is a little bit sad from my perspective in the sense that we claim that we have this really extensible translator system, which is true because they were able to add the Chisel support. But the way they did it was they forked Surfer and added the Chisel support, and it hasn't been upstreamed. Yeah. So there's a fork of Surfer called TieWaves that implements this Chisel translation. Any chance to merge it till February 2026? Possibly. I could. We should probably do that. The thing that has changed since that was written is we now support loading translators from WebAssembly dynamically. So I think the reason we also have a translator for Clash, which is in the same situation. It's been written, but it is a fork that I'm not sure is maintained anymore. But with these with WebAssembly translators implemented, we don't actually need these to be upstream. We can just say, here, download this WebAssembly binary, and it will be loaded. I just need a solution for second semester students using Windows machines, having no idea how to install stuff. Yeah. WebAssembly is simple to use. I should absolutely look into getting TieWaves properly integrated into Surfer. Yeah. Then I have small technical questions. Surfer, I think I will just file issues. Yeah. And okay, a final question. I've seen you have a guest lecture with Scott Beamer on his HL hardware course. Yeah. I'm doing a similar course this fall. Would you like to come to give a guest lecture on Spade? Absolutely, that would be really fun. Okay, great. Thank you. Thank you very much.
So now it's time for the examination board, and I suggest that we do sort of round robin, so don't drain each other's questions so quickly. So should we start from here?
Okay, so again, thank you for the nice presentation and the nice work.
Thank you.
I was really impressed. maybe one remark because it fits to the previous discussion. So I made the same experience that FPGA tools are really bad in doing retiming, except for DSP blocks. So that's why we did the same or similar approach like you in our tool Flopoco, which is a hardware code generator. So different from language, of course, but in an early version of Flopoco, we had something which was called next cycle, which is similar to your register, which simply says, okay, every signal until here was in one stage, and with next cycle you introduce the next pipeline stage. But after some time, it evolves that we got rid of it and do some automatic pipelining. And when reading your expression, like how you design or define the pipeline depth and then the registers, what about like maybe extending SPADE towards like an automatic pipelining system where you specify the depth of a module maybe, but put there something like automatic so that the compiler can do the job? Because if you have a good target, a model of your target, if it's FPGA or ASIC, then for every expression you can derive a delay and then make a delay-based pipelining that you get to the best speed you can have with this certain pipeline depth.
Yeah, I think that's absolutely something I want to explore. There's another HDL called Pipeline C that is built specifically around this idea, and I will ask you afterwards perhaps about how you do the model, how you get the model, because the way Pipeline C does it is it synthesizes it with the tool, looks at the critical paths inside pipeline registers, and then you have quite a long back and forth there. I also don't think Pipeline C has a specified depth, but it would certainly be very helpful because a lot of the time you don't actually care exactly what the registers are. And here my approach is essentially, if I can't figure out how to do it, give the user the tools to do it in a way that doesn't make them super frustrated. But if we can do automatic pipelining, that would be super nice, especially if it's like, we think this module can be auto-pipelined and this one can't, but you specify the depth and then everything else works the way it should. So.
Okay, thank you.
Thank you for a very nice presentation and a really interesting thesis.
Thank you.
As you might notice in a while that the committee is put together, we have some different aspects. We'll ask questions different. So I will mostly ask questions about programming language theory and compilers and related to that on this. So I'm interested in now to start with types.
Yeah.
And so in programming language theory is something called type soundness and type safety. And I noticed in your thesis you wrote about that you say that the language is strongly typed. And then I saw on page 37 that Scala was very strongly typed. So I'm curious about what the meaning of very strongly typed means, more than strongly typed.
I'm also curious about that now that you mention it. So I guess in general my approach, I've sort of picked up the type details and so on as I've gone along, which makes the time system kind of janky in SPADE. It seems to work, but I don't know if I can prove anything about it or anything like that. And that very just sounds like something I wrote and didn't think about.
No, but I'm curious about this with the type safety. So actually type safety and type soundness are typically used as the same meaning in our community. And I'm wondering, so in programming languages, not in hardware languages, there's typically that there's a definition, what do you mean by type sound? And a famous quote is that a well-typed program cannot go wrong. That is not a formal definition, but then you can formalize it using progress and preservation theorems, and then you prove properties.
Yeah.
And so on. So and in that way you formalize what is an incorrect program, and what are you actually guaranteeing when you say that you will reject programs by the type checker when they are correct. So my question is, in this domain, when you say that it's type sound, what do you mean by type sound or type safe? What kind of programs do you rule out?
Yeah.
And what kind of guarantees do you give?
I guess without having thought about it for too long, I guess in this case, it's you can never create a value that is not is not a valid instance of that type. So you can't create an option that has the wrong tag, for example. And you can't interpret a value as the wrong type, and you can't accidentally convert between different types without doing so explicitly. And there's escape hatches, so there's an unsafe block that you can create an option from scratch. But without the unsafe block, you can't have a value that has a representation that isn't a valid value for that type.
Right, and I guess it depends on now we've talked about option type, but if we go to pattern matching, for example, what kind of aspects do you have there?
So the pattern matching guarantees that all cases are dealt with, which again, I guess then relies on this fact that you can't create an invalid instance of a type. So the pattern matching, I guess in general, to answer this question, I just take whatever Rust does and just implement that. But yeah, pattern matching guarantees that you check all values. We could add a check that you don't have, or a warning that you don't have overlapping, or I think Rust calls them useless branches.
Exhaustiveness checking, yes.
Yes, so we have exhaustiveness checking, and we don't have the overlap check where we could implement it. But yeah.
Okay, thank you. Then I hand over.
Thank you. And thank you for inviting me here to read the thesis. It's a really nice thesis. I can congratulate you already now.
Thank you.
And it's interesting reading because, I mean, as David pointed out, we have different focuses here in the committee. So this is a large part of the thesis is a little bit further away from my area. So, but anyway, I would like to just say that I still basically do two questions here in one shot. I'm very impressed. I mean, and impressed by Spade in these things. I mean, it's I didn't know that you were doing things like this. It was really cool.
Thank you.
That you're doing it really from scratch and building it up. So that's not a question. So we won't count it like that. No, but I was very impressed by that.
Thank you.
So now. I work in optimization, so I think that is, I mean, it's also, of course, lots of optimization in compilers and so on. And then the idea here is also to have a language which is close to software language. Then one could think of that you basically, let's say you have a C-style language, which you can have both for software and then for hardware. Could you think of that you write a program in, for example, C, and then you tell the compiler that I have this amount of hardware space. Now, optimize performance. So what should be placed on hardware and what should be implemented, I mean, a traditional CPU, for example?
Yeah, I think there is existing research for that. You would then, I guess you would use this high-level synthesis thing which takes in C code. I believe LegUp, which is a high-level synthesis tool from the early 2000s, does precisely this of I think they run the C code, figure out where the sort of performance bottlenecks are, and in some ways decide what do we run in software, what do we run in hardware. So I think LegUp is the sort of first things that comes to mind that does this. It's not something I've explored.
No, but it's very interesting. I mean, one could perhaps also think about different criteria.
Yeah.
So I mean, you could optimize for speed, basically, as we just said, but perhaps also, I don't know, energy consumption or something, efficiency there. So.
Yeah. Hardware optimization is also always an interesting thing because in software, I would say you almost always optimize for speed. Mm-hmm. Sometimes you care about resource or RAM usage, but it's very much secondary to speed. But in hardware, you can always trade area for speed, and then energy consumption is kind of also a factor there. So it makes optimization non-linear or something like that, without you knowing what non-linear means.
Unfortunately, both non-linear and non-convex and horrible.
Yeah.
Okay, so then I hand over the mic.
Okay, maybe I stay there at optimization, but more looking from an arithmetic point of view. So I was wondering a bit how the backend is designed to generate the Verilog code at the end when you are using Spade. So There are like abstract functions like .sum I've seen in the FIR filter example that computes the sum. So I was wondering, okay, is it just like a sequential sum, like many pluses in a row, or is it like a adder tree? And yeah, the reason why I'm asking that is in our like Flopoco tool, why we are using code generators is to use or to make use of optimizations that could be in the synthesis backend but are not sufficient. So I was wondering if there would be a chance like to let the user maybe override such things, so things that should run at compile time and not at synthesis time. So would there be any chance to like make a different sum implementation using fancy compressor trees which need to be optimized, using fancy methods at compile time?
Yes. The sum method you mentioned is actually built inside Spade. It is not a thing the compiler has natively. So that is I don't remember if that particular function does a tree or a linear sum, but it is written using this recursive instantiation of modules things. So you as a user essentially have to define the sum type. You don't get the sort of default in the language. Or actually, I guess I, as the standard library implementer, implements the sum. Then I think it would be interesting down the line to have it be configurable, so you can select which sum implementation you want. It hadn't occurred to me that it might even be something that we want. But for now, it's whatever the standard library says for the sum, or whatever you implement if you implement sum on a different type.
Okay, this I understand, but my main question goes to this compile time optimization, which is, I don't know how to get there, but I can only imagine that you have to implement some Rust code in addition to get a recipe to design the actual hardware. So this is what we do in the code generator, of course. I was wondering if this could be possible with a nice Rust interface somehow to do these optimizations.
Yeah.
Not sure if it's the right place. As I mentioned, the best place would be the synthesis tool, but if they have a lack like that.
Yeah. For now, there's no way to run software code at compile time to generate hardware. It is something I want to do. It is essentially a macro system at that point. The interesting thing about the macro system here is most of the time, like the Rust's macros run on the AST level. But if you want the sum type to be macroable, you want the type information already. You want how big is the sum? What are the input values? Yes. So we would like a macro system that runs way later in the compilation process. And I haven't figured out how to do that, or if it's even possible. But it would be very nice to have. I just need to come up with a way to do it.
Okay, thank you.
So I want to dive into one specific language construct and try to understand it, because I have I don't really understand some concepts here, and maybe you can clarify this. So ports is the topic.
Yes.
And I read in the beginning of this, I made a note here, page 29, that they are bidirectional. And then I came to page 70, and then it says they are directional. And then there are these immutable and mutable ports.
Yes.
But the mutable ports are inverted.
Yes. Oh, right. Okay. So first of all,
so maybe there's many concepts here, and so maybe you can kind of straighten this out.
So mutable, first of all, that's a simple one to answer. I call them mutable. After some discussion with the rest of the community, we realized that mutable is not the right word. We want it to be called inverted. But my brain hasn't adjusted to that change, so I've sometimes written mutable when it should be inverted. So there's really three things here. You have a port, which is a collection of wires. And these wires can be, I guess it's a collection of other ports. And the sort of fundamental port is either a inverted wire or a non-inverted wire. And the invertedness refers to the direction of that the signals flow here. So you take you take a port, as an input, all the inverted parts of that port become outputs. But then you can also have an inversion of sort of part of the port, and then all the wires inside that are flipped.
Okay, so I guess then the first where it says bidirectional is a typo. They are always directional, either input or output.
Yes, but you can have a struct that has both inputs and outputs.
Right, it
And
nested
that's,
in.
I guess, what I meant by, I hope what I meant by bidirectional. Or maybe I just...
So another way of saying it, it's basically when you have the signature of the function, you have either an input or an output port, which would be called then inverted or non-inverted, right?
Yeah.
And then, but you can have a nested structure of these ports, so that means that you can have input and output nested in the same structure.
Yes.
Okay.
Yes. And you can also return a port. I guess that's worth specifying. You can return a port value, and then these things are also inverted. So then your inverted, or the things that are...
Are you returning the value, or is a port a first-class citizen? So you can actually report as a higher order?
I think it's something of a higher order, yes. So you return... when you return a port, you return the wires that you can connect up elsewhere.
Right.
For example, a memory can return, these are my 2 read ports. Give them to some other module that takes read ports.
But I guess you implemented some sort of reference that you're keeping.
Yeah, they are, yeah.
Okay, thank you.
Yeah.
Thank you. So, regarding this dynamic programming solution, I mean, are there alternatives to dynamic programming? I mean, I guess you basically got the solution. I mean, your focus has been on the hardware, so
Yes.
I'm aware of that, so I shouldn't direct the other questions here. But still, I mean, in principle, you could write this perhaps as some finite dimensional optimization problem, like using Casade or whatever, and then you will use online optimization for this to solve the problem. And I mean, the main work is then to compute the Newton step there, which is basically the search direction, which says that you should go in that direction and look for better numbers, so
Right.
to say. And then the question is, I mean, I guess you could, in principle, then accelerate that Newton step computation. Is that something you have been thinking about or seen?
So I don't know what the alternatives are. I don't remember what other options you have than dynamic programming, if I even read that at some point. From your brief description of this Newton step thing, it sounds like that's the step you take, and then from there you have to evaluate something else, and then you sort of step through.
In principle, you linearize the model where you are, so to say, or the optimization problem. Then you solve. You could see it as a dynamic programming problem.
Okay.
A Ricotta recursion, which is dynamic programming, which says that, well, from this linearization point, it sounds good, like you go in that direction. And then you change basically your input signals, you go in that direction, relinearize. Okay, now I have a better picture, let's go a little bit further in that direction. And this direction computation, I think, could be accelerated now.
Yes. So the problem with hardware acceleration is that you almost always want to exploit parallelism. If you can only do one computation at a time, your hardware is going to be run at 500 megahertz instead of 3 gigahertz on my laptop or something like that. So if it's like a relatively complex computation that can't be parallelized, and then you figure out, okay, from here on we need to do the next calculation, and you don't know what that calculation is until you've done the previous one, I don't think hardware acceleration is a good option here. So I guess it depends on what's in this step function, and if you can predict where you need to start computing next before you've done that.
And the point in your work is that you parallelize in the state space.
Yes.
Yeah. So what you can do here, I heard that someone here at Leo that's actually done that, parallelized in time.
Okay.
So you can basically half it in time and half it in time and half it in time. So you get logarithmic growth in the prediction horizon, which might make sense if you have 680 steps.
Yep.
So perhaps it's possible then to parallelize it in time instead.
Yeah.
Because there is no reason if you do this to parallelize it in the state space, because you're not exhaustively searching for it. You're searching locally all the time. That's
Yes.
the point.
Yeah, no, that sounds interesting. And if you can like divide it in time and start this one while running this one, I think you can also accelerate it quite a bit. So
Exactly. So that's the point, that you can work on different places
Yes.
in time and then tie them together.
okay, yeah, then hardware acceleration should work, and it sounds like an interesting technique for. Yeah, I can't say if that would if there are problems with applying that technique here, but
No,
if
of
there
course,
isn't.
of course. It's just the idea.
Yeah, but from a hardware perspective, absolutely, that could be done.
Thanks.
Okay, I also have to come back to the ports question because that confused me also a bit. Like from a programmer's point of view, I mean, it's fully consistent if you have a method that has some arguments and return values, then it's clear what is input, what is output.
Yes.
Then you like, define this inverse thing. Okay, first I was confused about the inf keyword because it sounds for me like inverting data, not inversing, or
Yep.
why don't call it just reverse, maybe?
Oscar has also pointed that out to me, that inversion can be, maybe we should consider renaming it again, and then I can say inverted, mutable, and reversed in the future.
Okay, so that was part of the confusion, and then I thought, okay, now you have a function that where you can pass arguments to that can be inversed.
Yep.
That means you can even flip return values and arguments by inversing everything. And then I thought, okay, is it maybe a bit artificially close to Rust to that? And why don't define like a port with inputs, outputs, no matter if it's like an argument or return value, or maybe use a different construct like function or method?
Yeah,
Let's
so
call it like entity thing or.
So the reason it is nice that the return values have the opposite flow of information is a memory, for example, that has some ports that it can expose, can return those ports, and then you can
understand
pass
why
them
you need
along.
this.
Okay.
It poses many problems.
Yeah, in some ways I think you are right that this is sort of following whatever Rust does. And the fundamental thing, I guess, is that Spade is very much a linear language, unlike Verilog, where you have wires going wherever. And so units, by default, take inputs and produce outputs rather than have a collection of input wires and a collection of output wires. And that, I think some people find that weird in a hardware context, of that's not really what we have. I'm on the opinion that that's the way I want to reason about things. I take inputs, I produce outputs. And then I realized that, well, sometimes I actually want to like not have these inverted things that go the other way, and then I had to add these inverted wires. And then now that we have methods in the language, this sort of default of you take inputs and you produce outputs means that we can have methods. I don't think you could have methods in Verilog in the same way because of this. So yeah, I guess the inverted things is a bit of a band-aid on top of that, but that also brings a lot of other advantages. And pipelines also wouldn't be possible if they were just a collection of wires. They have to have this flow from top to bottom.
Okay, so one has to more interpret the argument of a function as an input to a block and the return value as an output.
Yes.
Not input output with a direction, but like in the data flow sense.
Exactly, yeah. So a memory has both directions, but it makes more sense for it to return its port than take it in.
So, I would like to talk a little bit about related work. So, I think you had a very nice here introduction where you had a great kind of taxonomy of all these different languages. So this is always hard to summarize in different ways and categorize it in different ways. So, and when you talked about languages like software languages versus programming languages versus hardware languages, you talked about new and old and so on. So I want to first, this is my first part, question that a little bit. Is new always better than old?
No. I think in languages, there are certainly new languages that are not as good as the old ones in general. But I think if you have an old language, you're kind of stuck with the fundamental design ideas that they had originally. And as you build on top of that language, you can't really go away from those without breaking backwards compatibility. And so I think C++ is an interesting case because it's from 1985, but it doesn't feel like a language from 1985 today because it has evolved so much. And they've been able to evolve it. And the other languages like Verilog seem to not be able to evolve away as much from these fundamental design decisions that you kind of have to build a new language. So I guess new isn't necessarily better than old, but new allows you to try new ideas, and hopefully those new ideas are better.
Yeah. No, so it's often the fundamental ideas that you want, and good ideas, they survive over time.
Yeah.
So one category of languages that you kind of mentioned, you had STRL as in one of the boxes here, and that is in the category of synchronous languages. So synchronous languages is a pretty big topic in itself. It's grown up especially from the French community from the 80s and forward. And one language there is called Lustre. Are you familiar with that?
I've heard the name. I think I might even have heard it at FDL when I was there in KTH.
So why I ask about that one, because I think there's a lot of similarities in what you want to do, but it's a little bit different. I mean, it was not for hardware description directly. It's kind of also, but they have a clock calculus. So a type system where you can be very precise about defined and not defined values. And so
Okay.
So my question, are you familiar with that? And if so, how it relates?
Not more than I've heard of it and know it's kind of relevant, and then I guess forgot to read into it more while I was finishing the thesis.
So SCADE, maybe you've heard of.
That one I haven't heard of.
It's a big commercial tool now used for this, and it's based on Lustre.
Okay,
So I think this is relevant for something to look into also if you're looking at it in a bit more formal what you can actually do.
Yes, absolutely. I will have to remember to look into that next time.
Since you mentioned STRL in the other part.
Yeah.
Yes. Okay, good. Thank you.
Yeah, thank you.
Yeah. So this is a question, I think, about Cinnabar and in paper E.
Yep.
You write that this tool must be provided with sample inputs and outputs from this model, which are basically representative for use.
Yep.
And then, I understand that it's very important that these samples that it gets are really representative for the use, because otherwise it can produce worse result than desired in situations which were not covered.
Yep.
So, I mean, could this be an issue in a safety critical application? I mean, I guess this optimization of power is not really safety critical from that point of view. I mean, you need to pay a little bit more higher gasoline bills perhaps, but otherwise than that, it's okay. But could this be a problem? Or?
It could absolutely be a problem, yes. Because so for context, the way these inputs are used is to simulate at different word lengths and figure out what is the error in the result at these different word lengths. And then we pick or the designer picks a value that is a good trade-off between error and resource usage. And if these estimates, or if the inputs aren't representative in practice, your errors could be much, much larger. And then I don't think, as you said, I don't think this is necessarily a safety critical issue, because this wouldn't affect anything else. This thing would tell you need to drive really weirdly, but hopefully the system that is actually driving the car would reject this and say, I can't do these extreme maneuvers or something like that. So I think it would give worse results in terms of fuel efficiency, but I don't see it impacting anything else unless the system precisely follows this route, and then I think that has been misused. So.
But I also mean more in general, if you would use this tool for a more safety critical application. I mean, it seems like it's a bit critical that you actually find these worst cases.
Yes.
And I mean, this is strongly related to what we have been doing, which also David is actually familiar with. I mean, when we certify computation time and so on, it's very hard to find where is actually the worst sample, so to say. So I mean, are there tools to actually guarantee that you will find the worst case?
So that was going to be the next thing I was going to work on with Cinnabar before Spade became a thing that was more interesting to work on. So I wanted to look into not simulating this, but sort of statically determining what is the worst case error in the output, given that we have these inputs and then given that we have these computations and these word lengths, and then ideally optimize individual word lengths on individual computations. But I didn't get that far. But I think that if this system were to be used in practice, I would want that to be implemented first.
Perhaps one can start in the end that you have too much hardware, and then you cut away things that for sure you don't need.
But I think it's still a difficult problem to figure out what you need to cut away. But yes.
Yeah, it's a very interesting problem, which I saw some connection there.
Yes.
Okay. I had almost the same question, but maybe on top of that, about Cinnabar and this range analysis. So at some part you wrote that the data type is fixed for the whole processing, and later I figured out, okay, the integer part is determined like in a worst case approach, and the fractional part is more or less fixed.
Yes,
so
that's
you get
right.
A single parameter you tune.
Yeah.
The integer part, is it determined also by the simulations?
No. So the integer part is done with, I think I did a fine arithmetic in there. I might have done interval arithmetic. No, I probably did interval arithmetic. Okay. So the user has to specify the bounds on the top level inputs, which is usually very simple because it's like, what's the maximum speed the car can drive at? And then the tool figures out these are the word lengths we need in order to never overflow these values.
Okay. And for you mentioned in the Outlook that you need some better tool to look at all the individual data paths. I think apart from that, one other issue is also the rounding modes of the operations. So do you truncate, do you round correctly or maybe faithfully? What would be your approach to get to some good hardware results, taking this into account, like the word length effects and rounding modes?
Yeah, from what I remember, I just truncate in this project and didn't think about it more because it gets sort of integrated with the rest of the system, where you simulate and you say, okay, this is what happened, and then if the error is from truncation or from truncation being a bad idea instead of rounding, I didn't look into that. I think we would, there's a lot more to do in the selection of the sort of fractional part of those numbers that we didn't get to.
Okay, so I want to dive in a little bit about the design and implementation of the actual compiler.
Yep.
Which I didn't read so much about in the thesis itself, but of course you spent a lot of time thinking about this. So, if I understand it correctly, I mean it's a compiler, but as part of the compilation chain, since you have higher order functions, that is not actually, it's compiled away during.
Yes.
So I guess you have some sort of runtime in the compiler. So it's evaluating in some way, maybe? Do you have closures there?
There are closures, but so the way it works is, I'm not sure exactly how you would define runtime in this case, but it compiles everything from the AST to the HR and does the type checking on these. But it doesn't type check any generic units at this point.
So maybe I can rephrase. Is the compiler itself Turing complete, or does it guarantee termination?
It is not Turing complete unless the recursive and code generation stuff ends up being Turing complete. Which now that I say that out loud, it probably does. Until we added this this sort of, you can have a generate statement that is essentially an if based on a type, then I don't think we can guarantee termination.
So can you have recursion that happens at
compile time?
Compile time.
Yes.
Right. And you have if
Yes,
If-
yeah. So
and you have lambdas.
lambdas are not evaluated at compile time, but yes, they.
They're not. When is lambda invoked?
Oh no, I need to remember how that works. So
Because there are no lambdas in hardware, so I guess.
exactly, yeah. So it does, yeah. The lambda does get concretized at compile time. Yes. So in
It
that
sounds
sense.
like it's Turing complete, and you.
It does, now that you mention, now that you phrase it like that, this does sound very Turing complete.
And then I'm happy that you can say that it's not terminating, because otherwise you have solved the halting problem.
Yep, I don't think I've gotten that far.
Okay.
Yeah.
Thank you. So I was comparing paper E and paper G,
Yes.
which are both about this hybrid electric vehicle.
Mm-hmm.
And I see in paper E, the states are kinetic energy and battery state of charge.
Yes.
While in paper G, the states of vehicle velocity and battery state of charge.
That's probably an error in the paper then. It should be the former where it's kinetic energy, I believe.
That is what I also thought, because I was backtracking a bit and looked in the reference, and it seems like it gave better stability in the solution.
Yes,
If I understood
that sounds about right. I've just heard from Daniel that it's parameterized by kinetic energy, and then I guess forgot about that when I wrote paper G.
Something like that I was expecting. So
Yeah.
yeah, but good. That was clarified.
Yeah.
Okay, one question again to Cinnabar. So I recognize that you like to synthesize a circuit. You need to use certain constructs or library elements in Cinnabar. Like, for example, the if construct was different. So I think that you get always a unique return value.
Yes.
So
I think that might be in the first version of Cinnabar, the one that we talked about in paper E.
yes.
Then that was the case. Then it was a C++ library.
Okay.
And then with paper with paper F, we rewrote Cinnabar to take LLVM bytecode as the input, and then you no longer need to use those library functions for ifs and things like that.
Answers all my questions.
Okay.
Because I was a bit confused why this was necessary.
Yes, no, that was version 1 and version 2 essentially.
Okay.
So there's still some standard library functions like the interpolation stuff that is hand implemented, but from a user perspective, it's normal C++ code.
Okay.
Or any other LLVM input.
And it was a short question.
Yeah.
So then I want to talk a little bit about semantics. So a language consists of syntax and semantics.
Yep.
And then you have static semantics, typically a type checker that is kind of rejection semantics, and you have dynamic semantics describing the behavior. So your work does not contain any formalization of the semantics.
Nope.
Right? But nevertheless, I want to ask you, have you thought about it? And then the follow-up question is, what do you think is the purpose and strength of actually formalizing a semantics of a language?
Yes. So I haven't thought about it much. The reason I've thought about it a little bit because my understanding is if you want to start doing formal verification, then of course you need a formal model of the language. So if we wanted to go down the formal verification route, it feels to me that we need to also formally define the language, and that's why we would do it. For hardware design, I guess I don't see a reason you would need to do it. Perhaps there is one. I guess it's also helpful if you want other implementers of the compiler other implementers of the language. But for now, I don't see a reason outside of formal verification.
Right, but you're touching on it. I mean, especially for correctness. So
Yep.
typically you formalize a small subset to be able to see that what you are proving that should be correct is actually correct.
Yep.
It doesn't say that the implementation is correct, but it says that the formal ideas are correct. And the other thing is also, of course, if someone else should try to construct it, it needs to be described how does this language actually work. And
Yep.
informal example can be hard.
Yes.
Good, thank you. You
Yep.
answered my question.
Thank Thank you. So there was one thing that I was reading here. It's a little bit in my backyard, you could say, but when it comes to related work, you talk about nonlinear MPC, and I mean this is closely related to what you have done. And you write that a common technique for solving this is explicit MPC.
Yes, that's...
Is it common to solve nonlinear MPC problems using explicit MPC?
I have no idea, actually. I still don't fully understand what MPC
Why do you
is.
think I'm asking the question?
Yeah, exactly. I shouldn't say yes to that question. I know that. So no, given that you're asking it, probably no.
I mean, the nonlinear ones are not that common, but because it's hard to guarantee things.
Yeah.
So it's a nonlinear problem, so it's hard to say what is happening between, for example, samples and so on. I mean, you can just sample and then use some neural network and approximate it and sample and pray, you could call this. But so people are doing that, but I wouldn't say it's really the solution for nonlinear MPC. And then you say that I mean, you write that the gains are typically linear in this explicit MPC,
right,
for a nonlinear system.
Interesting.
Yeah, it's very interesting, actually. It would be very beneficial, because then I think more people would use. I mean, if you really talk about nonlinear MPC, then I would say in general the gains are not really linear. You would get some nonlinear function, and that's what makes it complicated.
That makes sense.
And you write that explicit MPC only works when the state space is not changing, which rules out this solution here, because you say that the state space is changing. And you point at then, I mean, changing velocity, speed limits, I would say. But, I mean, is that a problem? I mean, the changing state space, you mean that, okay, you're not allowed to be outside certain parts, so to say. Isn't that just a constraint?
Yeah, I can't argue with that logic.
So, I mean, as I said, this is basically on my backyard, and I didn't want to push it too much here. But I think it can be motivated in a slightly different way. I completely agree with you that you wouldn't use explicit MPC here. And the main reason is perhaps that it's very computational demanding. You would not use it for long horizons, which you typically have here. You could, I mean, you should use it in that case for some receding horizon solution, and then you really shrink the horizon, but then perhaps you can't get this look ahead. So the end conclusion is completely correct.
Right.
It's not really this tool for this problem, but perhaps polish the motivation.
Yeah, no,
there.
So the way I wrote this was essentially, I went and asked Daniel, my advisor, on the sort of vehicle stuff about MPC, and because Oscar and I realized this is probably MPC, so I talked about it with him a little bit, and then kind of felt like I had some understanding of what MPC is, and then read the literature, didn't fully understand something, and I'm not even sure if Daniel reviewed that paper even, so I'm not surprised there are issues with that.
Yeah, I mean,
retrospect.
Just for future publications, I mean, so you can polish it a bit there, so it'll be
great,
fine.
Yeah,
good.
Okay, I have to come back to hardware and synthesis.
Yep.
So, I really like the part about clock gating using the valid signal, and I agree to all of that, using either using enabled signal for FPGAs or the clock gating for ASICs. What I didn't fully understand is the part you introduced before, like multiplexing with an input which is don't care. So you have one figure that if data is not valid, you set it to don't care.
Yes.
I think it's around page 100.
It should be in paper B, I guess. Why are the papers so long?
Look at page 100 or maybe 99. Oh, it's 99. Yeah,
this one, right? Yes.
One, yeah. And later you wrote that you found examples where this is beneficial, but it was hard to reproduce.
Yep.
And To be honest, I don't get how it works. So, I mean, don't cares are, of course, a method to reduce complexity, but you change a function of like n bits that come out of the adder to a function with n plus 1 bits, because you include the tag, where like half of the function is don't care, half of the outputs in the truth table is don't care, but the other half remains the same as before.
Yeah.
So of course you can make it the function logically independent of the tag, but how can you improve it further? So
so we were really surprised by that result as well, where we synthesized a fairly big example and saw that this change from essentially from B to A or from A to B, which shouldn't affect anything, had a massive change. And yeah, we were discussing it. We couldn't think of a reason why. I tried to like reduce the size of the example, but I couldn't get the size of the example down to a size that was small enough to understand that also still retained the problem.
Okay.
It was also one synthesis tool. I tried it with Yosis afterwards. That didn't show this behavior. So there's something going on there, but I have no idea what.
How you came to that idea initially? So why did you think that it is beneficial to do B instead of A?
So B is what the spade compiler emits.
Okay.
And A is what a Verilog user would probably write.
Okay.
So we were curious,
more by accident then?
Yeah, it was. I was expecting no difference, and then got this massive difference when I was like, because that's the A is a more sort of, or B is a more naive or more complex way of compiling it that shouldn't affect things, but that makes it better. So yeah, it was completely by accident, and we couldn't find an explanation for why this happened.
Okay, so maybe it's just the fact that the synthesis is a heuristic that...
Yeah, something like that.
Where a different input might get to a very different output.
Yeah,
okay.
we at some point maybe I'll look into it, but for now it was like, okay, we can just leave this, shove it off to the side.
Yeah. So my guess is that synthesis did a really bad job before, maybe?
I think so as well, yes.
Okay, thank you.
So Spade can be seen as a domain-specific language for hardware. Right?
Yeah.
And you decide at some point to make it sometimes called like external DSL, that you're writing, your own parser, your own static semantics, and so forth. And the alternative that you touched on a little bit with Martin here is to make it more like an embedded DSL, like they do in Chisel, for example, when they embed it in Scala.
Yep.
So then often when you have embedded DSL, people categorize it in shallow embedding and deep embedding.
Okay.
I don't know if you're familiar with this.
I haven't heard the term, I think.
So shallow is that you can translate directly, basically, or deep is that you can reconstruct the AST, so abstract syntax tree, and then can do transformations. So you can kind of come back to some of the benefits that you actually have when you're creating from scratch.
Yeah.
So I was wondering if you could elaborate more a little bit about these design choices, the benefits, the drawbacks of embedded DSLs, the benefits and drawbacks of doing like you in external DSLs, and so forth.
Yeah. So I think there's a few different reasons you would do one or the other. I think, as me and Martin discussed, if you're building something like a generator, the big benefit in my mind of an embedded DSL in hardware, at least like Chisel, is you can write complex software code that generates hardware that you have lots of control over what you're configuring. And I think my favorite example of this is this Vex RISC-V core written in Spinal, where I've read that code, I've gone through layers and layers of classes, and I haven't found any hardware description anywhere in them. But it still works. It's a very high-performance RISC-V core. And if you want to do something like that, where you can have, like, you give a list of plugins for your processor, like you give it a prefetcher or a cache and something, and like just as a list of things, and then it figures everything out. I think it's very hard to beat the embedded DSLs in like I don't know if that's a shallow or non-shallow embedded DSL, but it's very hard to beat Chisel and Spinal and Amaranth in terms of generating hardware from a configuration. The downside, or I guess there's two downsides to it. One of them is it ends up being somewhat clunky in terms of, as I also mentioned with Martin, the good syntax is sort of taken up by the host language, and then you have to work around that, and you sort of have when otherwise instead of if else, which it's somewhat of a minor point, but it's still a point. And then you have error messages, which again, you have runtime errors that are now need to tell the user what happened, but it's not at compile time, so you may not have source references. So error messages and sort of that, the clunkiness is a problem. I think there's also things you can't do as an embedded DSL, like the pipelining system messes with the scopes of variables, and I don't think most languages that you would embed something in, I don't think allow you to do that in this way, maybe with macros. There's also another advantage of an embedded HDL, and that you get all the tooling. You have an IDE for Scala, and you don't have to build your own language server protocol. You have an auto-formatter that admittedly formats it weirdly because this DSL has weird syntax. But so yeah, I think those are my main thoughts there.
Very good. I think you touched on all the important points. The deep embedding, that's where you can do more analysis of, for example, name bindings of.
Yeah.
So that is.
I think there is, I know one example of a deeply embedded HDL, and that's Defiant, which I think I mentioned somewhere, and that does like use. It sort of repurposes, or it integrates with a Scala compiler, so you don't have a lot of these issues. But it's from talking to Oron, who developed that, it required a lot more effort to develop that part then. So.
No, but there are many benefits of doing it external as well. So
Yeah.
I totally understand your decision. Thank you.
Yeah.
So you write about or refer to a zoo et al. They have done some GPU implementation
Yes, right.
of this dynamic programming algorithm for hybrid electrical vehicles. And it's hard to compare, I mean, the computational performance because you didn't have the details and so on.
Yep.
But I mean, can you say something about power efficiency? GPU doesn't sound very power efficient.
Yeah, my guess would be it's less power efficient. I don't think, like we haven't measured the power efficiency of ours, and they haven't published the power efficiency of theirs, so I can't tell for sure, but I imagine ours is more power efficient because we don't have any control logic. We only have data logic in this case, at least in the vehicle model.
Because, I mean, it would be a little bit sad if it's basically better to kick out the hybrid electric than
Yeah.
just because it takes so much
Yeah.
energy to do the computations.
No, I've heard, initially my thought was like, you're driving a car, surely my little computer wouldn't be a significant contributor to power, but I don't think that is necessarily the case. And we haven't measured the power usage here, so.
Because I think it is a problem for autonomous vehicles. I mean, at least at the, how do you say, the prototype stage. I mean, they are consuming a lot. I mean,
Right.
if you have the entire trunk filled with GPUs,
Yeah, that's
it is a problem probably.
Yep.
So, I mean, I was also just thinking that perhaps, I mean, if I don't know how large factor there would be. Otherwise, you could always have at least argued and said, well, if it's a factor of 10 typically, then of course you could mention that.
Yes.
But, if it's like 5%, then of course it can be plus minus 5%. Then it's
Yeah, no, that's absolutely, we should.
I just thought that was one killer, so to say, argument there in
Yep.
some sense, even if it's hard to compare computational performance.
Yeah.
Good.
Okay, we are approaching to the end. Yeah, so one question about your hardware accelerator you implemented. So you showed impressive acceleration results, like 120x or so, like getting from this 2 minutes to 1 second.
Yep.
Yeah, but what about like the communication overhead? So you have to integrate your accelerator in some system. You have to communicate from the CPU to the accelerator. From what I read, you did not take this into account in your overall speed up measurement, but how much data is it to communicate, and what do you expect like in drop of acceleration due to this overhead?
So I don't remember. Yeah, no. So I think what you would need to communicate is the the speed limits and the state of charge limits. I think the state of charge limits are fixed, so you wouldn't have to communicate those. So you would essentially have to communicate the bounds on the speed limit in order to start the computation. Getting the results out,
Can you give it a number of bytes or so?
Yeah.
Is it hundreds, thousands?
It would be it would be low thousands, I think. So it would be, say, a floating point value for the top and the bottom of the speed limit at every distance step. So it would be 512 times 32 times 2. I think the more interest or the more difficult one is getting the data out. I don't remember how much we mentioned of this in the paper, but once you've done this, we compute the cost to go map. What you then want to do is run the algorithm forwards in order to figure out exactly how to follow this map since it's discretized. And then you kind of need access to the full cost to go map. So I'm imagining the way you would implement this in practice is one of these sync FPGAs or something like that, where you can have a processor that has access to the same memory. So we write the results into memory that the processor can already access, and then I think the transfer overhead wouldn't be that bad. And then you just have to run that software computation at the end.
And I believe it can be hidden in the computation time, maybe in this 1 second.
Yes, you could absolutely start preparing the next one before the previous one is done. So.
Okay, so I think I'm approaching my last question here. So, and that would be about type inference. So I've just read a few quotes that we can start with.
Yeah.
So on page 65, you said spade is a statically typed language with type inference.
Yep.
And then you said that next page, finally, unlike language like Haskell, spade does not do whole program type inference, which is why all the types are the unit and are specified in the head. And then on page 70 you say, therefore spade has a type system that is more powerful than most contemporary HDLs.
Yep.
Right, so these are some claims there. So I was wondering, what do you mean by type inference?
So I mean that in as much as possible, the compiler can infer what types are used based on context. So you don't have to write out type signatures for most things. And the thing I meant with the second quote of whole program type inference is that I think in Haskell you can have a top-level function that doesn't have any type information, and it sort of gets type inferred with the rest of the program. In Spade, I force users to write a full type signature in the inputs and outputs. And then inside the body, you don't have to write out types because they are inferred, unless the inference can't figure it out.
Okay, so if you go to page 66, just
Yes.
looking at an example here.
That is not...
Actually, it doesn't matter, it's just some where you have a signature.
Oh, I think, yes. Yeah, this is a signature.
This one works, yeah.
Yes.
So here, so what you say is that you need to give type signature of the top level.
Yeah, exactly. You need to give these types,
Right.
but the X here you don't have to give because G, it knows what G returns, given that you pass A. The multiplication will produce a 64-bit integer, since these are 32 bits, you don't have to write that out. This will be whatever F, or F and X have to be the same, and then plus 1 will be the sum.
Oh, right.
And then it checks this. And that's, I think it would be feasible to not require type annotations in the head as well, in some cases, but I take the same decision there as Rust of these are useful for documentation, so force the user to write them there, even if maybe the type inferrer could infer those as well.
So just when we talk in programming language theory, type inference is when you're inferring the signature. So, so that is basically when, because other ones you get directly from the types, you just have the terms and then you can derive them directly. So when you have type inference, you typically need to set it up as a constraint solving problem and then solve the types. That is what's done in Haskell, for example, or
Okay.
camel. So that's
Is Rust not type inferred then, or?
not in that sense. No.
Okay,
So
interesting.
it's basically. I know Scala sometimes called that they type inference, but it's the same thing. It's just derived directly. So.
Okay.
So there are pros and cons with these concepts, but there's so many details in getting it right when it comes to type inference. That's why I was curious. What have you done there?
Yeah. No,
Because so this would be often referred as explicitly typing. So you explicitly type the type signature, and then when you derive the types, you always have them.
Okay.
And go forward.
Yeah, I guess one question then, even if this would be generic, so that if X is generic over, say, instead of 32, it's generic over N, would it still be explicit typing, or do you get towards typing?
Yeah, because you're explicitly saying which type variables you have.
Okay.
Right. And that is the tricky part with let problem. That was kind of the foundations of ML, that they can do inference even with parametric polymorphism. So
Okay.
But I think the design decision is very pragmatic, and to not that, because there are pros that becomes, you have a bit more verbose, you have to write it out, but it's also good documentation.
Yeah.
And it simplifies a lot your way of getting
Yes,
there.
the type inference is hard enough to write without having to do full program things. So.
Okay, good. But then I understand what the statements that you stated.
Yeah.
Thank you.
Yeah.
Thank you very much.
Thank you. So again, in paper G, it's about this model that you have there. I mean, you parallelize, as we said before, in the state, and then they write that perhaps splitting can be done such that one functional unit then takes the same branch in an if statement.
Yes.
But isn't that, I mean, if I'm thinking about the model, which, if I understand it correctly, is called in every sample to propagate to the next. I mean,
Yeah.
Isn't it very hard to know, because you have parameters also to that model, or is it easy to say that this state will always result in this, so we can remove?
Yeah, so I think it depends a little bit on what which if statement you're in. For example, I think in the model there's a quite early if statement that is the torque from the combustion engine positive or negative? Because if it's negative, we're braking instead of we're mechanically braking, and that would be very simple to take out to have split the state space at the velocity, and have one instance of the model that only does braking, one instance that only does combustion engine acceleration. If you have an if statement later that is dependent on other things, this is of course a lot more difficult. But for the simple case where there's an if statement on early inputs, then you could absolutely do the split.
Yep. Yeah, I agree to that. So, I mean, I think I was thinking about, I mean, the optimization problem, but you're talking about only the model, so to say, the physical model. So, I mean, constraints and so on, these are outside.
Yeah.
Because otherwise, I was thinking parameters in this case is, for example, they are changing, as we said before, speed limits and so on. That could also affect which path you take through the algorithm, but that's not here, so to say.
Yeah. The splitting here is because we're generating hardware both for the if branch or for the true branch and the false branch. If we can guarantee that one instance will never be called with a true branch, we can eliminate the hardware for that and save resources.
Cool. So.
Okay, maybe a very last spotlight question. So you wrote that Spade also inspired other languages, which is already impressive. Looking at the short time Spade is existing.
Yeah.
Maybe can you comment on that, the feedback of the community or other research groups? So there's a lot of dynamic in there. So what languages were inspired, or?
Yeah. So the one language I know for sure was inspired by Spade is one called Sus. I think that was 2 years ago that the person started working on it, and he essentially doesn't like my pipelining system and prefers to have the latency of a variable instead of explicit stages. And so his language doesn't have the pipelining system, but it has a system that solves some of the issues that pipelining brings. The other language that I think I mentioned in that section is Filament, which, as it turns out, was presented on the same workshop I presented Spade, or at the parallel workshop to where I presented Spade for the first time. And then since then I've collaborated a lot with Rajit, who does Filament. He knows a lot more about type systems than I do, and I guess the pipelining system would be the filament type system if I knew how to implement a type system. But we cannot, in Spade, we can also sort of get away from the type system filament isn't as general as Spade. And then we've had there's another community where I started talking about Spade with other HDL developers, so we have a nice discussion there, and we have a lot of the languages I have in my related work sections are specifically from that community where we sort of discuss, oh, this is a new one we haven't seen before. What's it about? Can we invite the author there? So it's a nice community.
So I just want to ask a last question, non-technical question, and this
Yeah.
is a kind of a classic, it's called professor question, because it's very generic, so you can always ask in any defense.
Yeah.
But it's still an interesting question, or interesting answer. So if you would redo your work, what would you have done differently?
Yes. So I think for both Spade and Surfer, there's not a lot I would change because the projects have kind of well exceeded what I expected to get out of them. So yeah, I wouldn't want to mess too much with that formula. Maybe I think for Spade, I would have liked to have a better foundation on the type system and not just make things up as I go along. But other than that, both of those projects have been way more successful than I thought they would be. For Cinnabar, I think there's a lot of interesting research left. We touched on that with the word length inference, that like how can we find a way to do word length inference that guarantees that we don't have a certain amount of error and so on. So I guess there's a lot of stuff I would have loved to do with Cinnabar if Spade wasn't more fun to work on. But yeah.
Thank you.
Yeah, thanks.
Thank you. So David, he stole my last question.
You have to come up with a different professor question.
Yeah, exactly. I'm fortunate that there are such. So
There's a hierarchy.
So I mean, which result are you most proud of? I mean, what?
Yeah. I think I'm most proud of the fact that Surfer is like being used by so many people and is actually useful in industry. It's super satisfying to get people message me saying, "Oh, I love Surfer, I love using it," or "Oh, we used it in our product." And yeah, so I think that's the one I'm most pleased with. And then I'm really happy that I'm like been able to find a niche for Spade where I can evolve a language that it seems like a few people are also interested in those ideas.
Very good. I mean, I'm also impressed and very happy for you that people are using it because it's not always the case. What is produced by PhD students and so on. I mean, it's very good work, but then it's just forgotten. But in your case, it's really used. So
yeah.
Congratulations to that, and
Thank
congratulations to a very nice thesis. So thank you.
Thank you.
Now it's time for questions from the audience. And also, if someone is on the online meeting, please type your questions and I will try to read them up. So any questions from the audience? I will run with the microphone.
So going back somewhat to a couple of the early questions you had on the matter of, for example, automatic pipelining or generalized, shall we say, optimization for various purposes. It seems that this goes back very much to the strictness of the language in a sense, and that the solution would be to move to towards something more like model-based design or requirement-based design. And this strikes me as very much an aspect of traditional programming, where we have a very descriptive, implementation-focused syntax. Are there any other aspects of traditional software design which you see any, shall we say, drawback to bringing over to hardware design? Obviously, you've covered the subject of what can we gain out of software design, but are there any pitfalls? So
yeah, I think the main one I can think of off the top of my head is in software you can often sacrifice performance for ease of programming. And in NHDL, I don't think you have that option. So I don't think we can, like, there's no way to bring dynamic typing over to software or to hardware, sorry. Or, yeah, really any abstraction that sort of breaks the, well, there's the simple thing of any abstraction that contributes overhead, but there's also, it's dangerous to bring over abstractions that don't necessarily contribute overhead, but that just make the hardware unpredictable. You want, generally you have an idea in your head about what you want your hardware to look like, and if that idea is wrong and the language does something weird, especially when you're an HDL that lies on top of Verilog, the step from my hardware is larger than I expected to what causes that in my input is very long. So you want to minimize that. You want to have predictable results as far as possible. And that's not necessarily a requirement in software.
Thank you. Excellent answer.
Thank you.
Yeah, you have made it very clear throughout this presentation that Rust was a clear inspiration for Spade.
Yes.
And I believe you mentioned at the very beginning of this presentation that the ownership model wasn't actually carried over.
Yep.
I was wondering, was there any kind of reasoning for that? Does it have a place in the hardware?
Yes, and I meant to say that in the slide about abstraction, but I forgot about it. So the ownership, so my point with abstraction is you want to hide the unimportant details and you want to highlight the important details. And the ownership model in Rust does that really well, because the software view of memory works the way it does. You have references and you have pointers. In hardware, memory is a very different concept. And also the way Spade is executed is extremely different. So that abstraction wouldn't work at all in software. We take the same idea with the linear type system for something else, but the ownership model it's a well-designed abstraction for that specific problem, but it can't be taken to another problem in a simple way.
One thing which we touched on earlier was the fact that you can have the inverted wires where you have outputs acting as inputs and fun stuff like that, and that seems like I don't know. Did you ever consider having some kind of message passing abstraction instead, like Erlang? You know, you send a message, you receive a message, and you have a more explicit way of saying you send this, you receive this, instead of having functions which return things and take parameters.
I think that comes back to this problem of, I don't know if there's a predictable way to design hardware for that. That message passing has to be implemented in hardware in some way, and maybe there is a way to do that in a good way, but then I want Spade to be able to describe general hardware, and then having a message passing system inside the language is problematic. So I think that if you want message passing, you should implement a library that implements message passing in a way that makes sense for hardware. And then because the type system allows you to build abstractions, you can get this message passing thing, but it shouldn't be a feature of the language. It should be something implemented in the language.
Right. Thank you.
Yeah.
We have one question from the chat as well, and the question, I just read it from my head. Have you used Spade for this vehicle model and for the compute architecture?
Yes, perhaps I wasn't clear about that. So in the vehicle model, we use Cinnabar, in the end, we actually use the commercial HLS tool because it's easier to compare results. So the vehicle model was implemented with HLS, and then the surrounding logic, the scheduler, and so on, that was implemented with Spade. So it was a combination of the two.
Thank you. No further questions, no. And I think that concludes the public part of the defense. So now I think someone might take the lead to where you all will have to wait, and the examination board and opponent and supervisors will reside to a room, and the examination board will discuss the outcome of this. And then we'll come and announce it. So some volunteer from... Yeah, follow Mikael. But first, let's give everyone involved a new hand.
Thank you all for coming.